So today we're talking about differential equations and specifically solutions that end up being exponential growth or decay. Oops, that's a typo. Exponential growth or decay. All right, so we have equations that look like this. They have both a x in them and a y in them. All right, what we saw yesterday is that we can rearrange things, okay, separating so that we have the y's together on one side and the x together on the other side. So we end up with something like this, y prime equals 2x. We integrate both sides with respect to x. This is the same as dy, right? And the other side is 2x dx. And then we had a lengthy conversation yesterday about the fact that the integral of y dy is going to be the same process as the integral of x dx. Okay, why aren't things moving for me here? Okay, so the integral of y dy will leave us with y squared over 2 plus c, 1 we'll call it, and the integral of 2x dx will leave us with x squared plus c2, and then we discussed how these c's, we can just clump them together into something else we call c. So final answer was 1/2 y squared minus x squared equals c. So we write it in general form. If we multiply everything by 2, so we have no fractions, we get y squared minus 2x squared equals c. Again, we don't write 2c because the c is just some constant. It doesn't matter if it has a number in front of it or not. Okay. If we wanted to check this, we would use implicit differentiation. Remember, that means take the derivative of both sides. If you take the derivative of a y with respect to x, you have to use the chain rule, okay? All right, so that was example 1. All right, we left off yesterday talking about how we can solve a specific type of differential equation where the derivative is directly proportional to the original function, okay? So dy dt is directly proportional to y, and we said we could do that, we could turn it into an equal sign if we have this constant k in front. So dy dt equals ky. The solution, or a solution to this, is always y equals c e to the kt. All right, and this makes sense because the derivative of e to the something always involves another e to the something, which is what we're saying up here. The derivative involves the original function, okay? So we were just about to try an example of that using, talking about radioactive decay, okay? Note that this gives us either exponential growth or decay. What does the growth or decay depend on?
The C.
Nope.
The K.
The K, what about K?
When the K is positive is growth, and negative is decay.
Perfect. Okay, if K is positive, we get growth. If K is negative, we get decay. Okay, so we're going to talk about radioactive decay. All right, so here's our problem example 3. We've got 3 real world problems that we're going to go over today, starting with this one. So we start with 10 grams of the plutonium isotope, and we talked yesterday about what plutonium is, what's special about plutonium.
It's like have the radius. What is that?
It's radioactive.
Yeah,
It's radioactive. It is a substance used for nuclear weapons or energy or whatever, okay? So our isotope that we're dealing with here, isotope means the same type of atom but different numbers of what? Different numbers of?
Mass.
neutrons,
Neutron, yeah.
okay? So we have a specific isotope, Pu-239, okay? And if we look at the periodic table, wait a minute, that doesn't make sense. Oh, no, that's not Pu. Where is Pu? 244. Wait a minute. Okay, we'll go with it. All right, plutonium-239 was released in the Chernobyl nuclear accident. How long will it take for those 10 grams to decay into 1 gram? Okay, and what I told you yesterday was that all elements have a half-life. Okay, a half-life tells us how long it will take for half of that sample to disappear. Okay, so if the half-life of this substance, which I've got a typo here, because up there I have Pu and here I have Pl, and that is incorrect. It should be Pu, not Pl, right there. Pu-239. The half-life is 24,360 years. That means if we started with 10 grams, if we wait this amount of time, we'll have only 5 grams. So after 24,360 years, we'll have 5 grams instead of 10 grams, okay? But before we go into that, let's talk about how we can talk about the rate of decay, all right? We know that the rate of decay is proportional to y. So change in y is proportional to y. So dy dt is proportional to y. And as a reminder, we can get rid of the proportional and put in an equals if we just add a constant. Now, we know that to be true. We also have some initial conditions, right? We know that at time equals 0, we have 10 grams, okay? We want to know at what time will we have 1 gram, all right? So, do we have any other initial conditions?
Yeah, it's like after this much years, then it will be 5 grams.
Okay, using the half-life, we can say that after, 24,360? 24,360 years, so I had to write it a little bit small, we'll have 5 grams. So again, so we have 2 initial conditions, and then what we want. As a reminder, for these problems, you do have to have 2 initial conditions to solve them. Okay, so we take this fact over here, that dy dt is proportional to ky, and we're going to say y means the amount of plutonium, okay? Y means the amount of plutonium. A solution to this then is y equals, what is it? Yeah, CE to the KT. That's our solution. It's going to be an exponential function. Now we have to figure out what is C and what is K. First step, what is C? Good. So we plug in T equals 0. All right, that will make this part turn into 1. That leaves us with C equals 10. How do we find K? Oops. You're right. Yeah, sorry. 24,360 up there, and that will equal to 5. All right, so if we want to solve this before, we could plug it all into our calculator, but let's go ahead and go through the steps it takes before we get there. Divide by 10, that'll leave us with e to the k times 24,360 equals 1/2. What do we do to both sides to get k? natural log of both sides. All right, that's going to get rid of the ln e. Okay, so 2, 4, 360 k equals the ln of 1/2. K is 1 over 2, 4, 360 times ln of 1/2. Is that right? Okay. If we plug this into a calculator, we get about negative 0.000028,454. Okay, so pretty small number there. All right, so our final model that we'll write is y equals 10e to the negative 0.00028,454t. Okay, so that's the function that solves our differential equation. Remember, y means what?
I mean the grams.
Yes, the amount of plutonium in grams. Okay, so now our question is, when is the amount 1 gram? How do we solve that? Oops. I broke it. There we go. Okay, that's amount of PU. All right, so set it up so that y is equal to 1 and solve for t. Okay, do you expect this number to be, what kind of value do you expect to get, like range-wise? Greater than, less than what the numbers that we've seen already?
Greater. What do you mean if the y on t1?
So taking a look at our other conditions, we expect it to be bigger than the 24,360, right? Because 24,360 years is when we have 5 grams, so it's going to be some later time, right? All right. So solving, divide by 10. And then what are we going to do next after we divide by 10? Natural log of both sides. All right, so ln of 1 over 10 is equal to, remember what this is in non-decimal form? Ln of 1/2 times the half-life, which is ln of 1/2 times 1 over the half-life, 24360t. So then to solve for t, all right, we're going to divide by the natural log of 1/2 and multiply by 24360 on both sides.
Why do we need a 1/2?
That's from, if I turn this decimal back into what it was before.
For the half-life?
But remember here, k is this. Okay? So I'm just taking k and using numbers now instead of the whole decimal. You could leave it as a decimal, but okay. So over here, multiplying by the half-life, 24360. Do that all out and solve for t. You get 80,923 years. That's a long time. Okay. All right, another application of these models is population. Okay, so a lot of times population experiences exponential growth or decay. All of these, hopefully, we talked yesterday about how calculus applies to your life. And, if you're doing any kind of business modeling or economic modeling or even like city planning, all of these kinds of models can be used there. So hopefully this is a little bit of inspiration for why to study calculus, okay? So here we have, now this is population of fruit flies. This is more application to biology. But fruit flies, you guys know what fruit flies are? Tiny flies that come on your vegetables. Yeah, they end up in your house and buzz around, okay? Not regular flies. But they are often studied in biology, especially for genetics. They're studied with genetics, so some have red eyes, some have white eyes, black eyes, wings.
I know.
You know about those?
Yeah, because in China, like teacher explain like your offspring.
Yes. Do you actually do it? Do you breed them and everything?
No, we don't do the experiment.
Okay.
Just tell us.
In college, a lot of times you do, and you have to like stun all the flies, so you don't kill them because you have to be able to breed, but you put them in this thing, and they all stop moving, and you can count how many have what, and then move on. So, all right, so important to biologists as well here. All right, so we have some fruit flies, and the population is increasing according to exponential growth. After the second day of the experiment, there were 100 flies. After the fourth day, there were 400 flies. How many flies were there originally? Okay, what kind of value do you expect that to have?
Lower than 100.
You got it. Okay, so let's go ahead and write these as data points. Okay, what is your x and what is your y?
X is the day.
Okay.
Of the month or day? Or day.
Just how many days? Change in days. Okay.
Yeah.
So after 2 days we had 100, and after 4 days we had 400. So we have 2 data points there. They told us that it was increasing according to exponential growth. So we know that the number of fruit flies, FF, we're going to call it Y, will be equal to what?
Y equals how many flies?
Yes, but what will it equal? What function will it equal? CE to the KT. That's our exponential growth function, okay? All right, now to actually solve this actually doesn't involve any kind of derivative. They're not giving you that information. We would assume that dy dt equals ky, but it's not necessary a step for this problem. But okay, we know this is our solution. Now all we have to do is use our two data points in order to solve for our constants. But we'll notice this is different than our other problems. In our other problems, one of our data points always involved 0. But in this case, we don't know what the original population is at 0. Okay, so it's a little bit trickier. All right, so let's plug these in. We know that when y is 100, when time is 2, and y is 400 when y is 4. All right, I have 2 equations and 2 unknowns. How do I solve for the unknowns?
Can you like divide both sides by c, and because the right equation is like 4 e to the 4k, and the other one is e to the 2k, so it's like a square of the first one.
Sure. Okay, so the basic idea is to solve one variable in terms of the other. Okay, so let's do that. Let's solve for c using this guy. So c, according to here, would be equal to 100 divided by e to the 2k, but dividing by e to the 2k is the same as e to the negative 2k. You guys okay with that? All right, so now we're going to take this value of C and plug it in over here. So we get 400 equals 100 e to the negative 2k times e to the 4k. All right, now we can see we can solve it pretty easily. All right, so this is going to be 4 equals e to the 2k. So ln of both sides, 2k equals ln 4, k equals 1/2 ln 4. Okay with that? All right. Now that we have k, we still have to go back and solve for c, and we can do that by plugging into this equation that we already have for c. Okay, so you plug in, you can calculate that. I just realized that I guess there's a slight typo in the book. They say the initial condition is 300 flies.
Oh, 300?
Okay, it doesn't matter. The process is the same, but the numbers they have in the book are not going to be the same as what we have, so I'm not going to write those numbers down.
If it is like 400, we can just use a very simple equation. No, the first day is like, because the second day is like 100.
Mm-hmm.
So it's like there have 2 times, or no, the second day is 100 or 200.
Second day is 100.
So the first day should be 50, because it's like it's 2 times the first day.
Let's double check. So originally we want to know how many we started with, right? Which according to our equation is what variable?
What? How many?
Yes, but it's the first day, on the first day. Which part of our equation tells us how many there are on the first day? Our initial. Think about our plutonium, right? We had 10 grams. Where did the 10 show up?
10 grams. It's just like
It showed up at our C, right? When T is 0, all you get is C. So our number that shows up on the as our initial thing, whether it's initial population of fruit flies or initial amount of plutonium, it's C. So I'm solving for C now. E to the negative 2 times K, which we solved for 1/2 ln 4, times 100 is, what'd you say it should be, Tian?
50.
Okay. I think you're thinking of
50 times 2 equals 1.
doubling.
Yeah, yes.
Okay. It's not doubling each time, it's exponential. It's e to the x. All right, it's actually 25.
But it didn't say like, how is it? But it didn't say, it's like 2 can make 1, so.
It said it's
Twice.
increasing according to the law of exponential growth, which means e to the x. So it's not just doubling each day, it's e-ing each day. Does that make sense? E is slightly greater than 2. Okay. All right. So, on the initial population only had 25 flies. After 2 days, it's increasing by a factor of, factor of 4. Interesting. Okay. All right. So, our final answer would be 25 for this problem. Okay. Any questions? All right, let's take a look at example 5. We're talking about sales. All right, so again, if you're studying the economy, studying business, this is another way that calculus can apply. Now, this you probably saw in pre-calculus anyway, looking at exponential growth and decay, but we'll take a look at how we can apply it now. All right, here's the problem. A company stops advertising. 4 months later, they notice that their sales have dropped from 1,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, so exponential decay, what will they be after 2 months? Okay, so what are our initial conditions here?
Like start initial units per month is like 100,000 units.
Okay, so when time equals 0, when they stop advertising, they were selling 100,000 units per month. All right, what's our next data point?
4 months later, it's like 80,000 units per month.
Okay, so after 4 months, so 4 and 80,000. Okay, so 0 and 100,000, 4 and 80,000. All right, if it follows an exponential pattern of decline, what function do we use?
We go C to the T, KT.
Okay, y equals CE to the KT. And the problem we're trying to, I'm sorry, hold on a minute. 4 months after it stops advertising. It drops from, okay. Okay, after another 2 months. So what is the data point we're looking for?
6.
All right, when t equals 6 months, what is y? Okay, what does y mean in this particular problem?
How many units per month?
You guys are pros. Okay, y is number of units per month. All right, so we have 2 initial conditions. This one's a little bit more straightforward than the last one because we have a condition about t at 0. All right, if t is 0, then we always know exactly what c is right away. What is it?
100,000.
100,000. All right, easy enough. Now we can use our other condition here to solve for k. So our other condition is that at 80,000, we have e to the k times 4. All right, so divide both sides by 100,000. I'm going to abbreviate 100k. All right. And then what else? What's the next step we're going to take? Take the natural log of both sides. So this is going to be reduced to 0.8. So the ln of 0.8, or the ln of 8 over 10, sorry, is going to be equal to ln of e cancels. We are left with 4k on this side. So k is equal to 1/4 ln of 0.8. All right. If we plug that into a calculator, we get a negative 0.0558. Do we expect that?
Yes, because it's decrease, it's drop.
It's decay, right? Decay, get it? K is okay, anyway. All right, so K is negative, so it's decay. It's exponential decay. All right, so we're plugging that back into our function here. Y equals 100,000 e to the negative 0.0558 times t. We're plugging in when t is 6. All right, when t is 6, calculate that. Put it in your calculator. It's 71,500 units per month.
Not pretty bad.
They're losing business, though. That's pretty significant to go from 100,000 to 71,000. What percentage have they lost?
I'll have it lost like 20 something.
Like 20 something, yeah, almost 30, right?
20 something.
20 something percent of their business. That's fairly significant.
Yes.
Okay. That's a lot of money, or can be, depending on what they're selling, I guess. Okay. All right. Any questions on that one?
This one is easy than example 4.
Okay, these are all pretty easy. You don't actually have to solve any differential equations for these last two. You just see that they tell you it's exponential growth or decay, and then you know right away that means C equals E to the KT. All right, since we've got the time, we are going to look at example 6. You're probably going to want to reference your book as we talk about this. It has to do with Newton's law of cooling. It tells us that Y is the temperature in Fahrenheit for some object. It's in a room, and the room's temperature is 60 degrees Fahrenheit. The object cools from 100 degrees Fahrenheit to 90 degrees Fahrenheit in 10 minutes. Okay? As the object cools, you have to know what's going on scientifically, and this is great timing for what we're learning in chemistry, right? Where's the heat going? Well, it's going from the object or the system to its surroundings. So as the object cools, the room will actually heat up, okay? Also, the colder it is, the longer it takes to cool, okay? And vice versa, the hotter it is, the faster it cools, okay? How much longer will it take to decrease to 80 degrees, okay? This should be greater than 10 minutes, okay? Because it's colder now, it's going to take longer for that to diffuse, all right? Newton's law of cooling says that the rate of change in temperature of an object is proportional to, dy dt is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So what it's the temperature of the room it's in. So it's not just related to its own temperature, but it has to do with the difference between its current temperature and the room that it's in. So in this case, it would be Y, the temperature of the object, minus the temperature of the room, which is 60, okay? And again, to get rid of that proportional sign, we can put in equals if we have a constant here. So now we have our differential equation, dy dt equals k, parentheses, y minus 60, okay? Now we can integrate both, now we want to separate, just like we talked about before. Put the y term on the other side, and we can treat this like Leibniz notation and put the dt on the right side, okay? So dy over y minus 60 equals k dt, okay? We can integrate both sides, and again, since the y matches the dy, this gets treated just like it were an x, okay? So dy over y minus 60, what does that look like? What kind of integral does that look like?
Oh, the natural log.
Natural log, right? So the bottom is our u. What would our du be?
dy.
Just dy, okay? So our integral will just be natural log of the absolute value of y minus 60. On the other side, we have k dt. K is just a constant, so the integral is going to be kt plus c, all right? Now, what we're trying to do here, is find out at what time will y be 80, right? All right, so in order to figure that out, what are our next steps here? Okay, so yeah, before we can solve that, we have to find k and c, all right? All right, so the first thing that might make it a little bit more convenient is to rewrite in terms of e instead of the y being inside the natural log. So if we do e on both sides, all right, we end up with y minus 60 on the left and e to the kt plus c, all raised on the right. Okay, everybody okay with that? Y minus 60 on the left, and then e, all kt plus c, all raised on the right. Okay, you may remember that when you have addition here in an exponent, it's the same as multiplication. This is e to the kt times e to the c. And once again, we treat this constant as just any old constant. So e to the c is just some other constant, just like something we call c. So we can actually call this whole thing c. All right, so CE to the KT, that's real convenient. And then y equals that plus 60. All right, so we've solved for y, made it look a little bit nicer. All right, now we need to solve for c and k. All right, our initial condition, when time equals 0, what is y? It's our initial temperature, 100, right? So C equals 100. All right, that we can do that without going through all the steps, right? Okay, so now we can solve for K. 100 e to the K. What condition are we using here? The other one, right? So at T equals what? 10, right? At T equals 10, Y is 90. Now we can rearrange and solve for K, and for the sake of time, I'm just going to flip through that, okay? K is negative 0.02877. Is that true? Is that what we expect? Why do we expect K to be negative? What's decreasing? Decay. The temperature is decreasing, right? All right. So now that we have our final function, y equals 10e to the negative 0.02877t, all right, we can easily solve for when y is 80, what is t? And it is going to be 24.09 minutes. I know we're out of time. So, all right, that's it.